This meeting is being recorded.
So today we're going to we'll try to do two things. So the first is we'll see what is the involution principle, which gives a bijective proof of the Rogers-Ramanujan identity. As I mentioned, the proof is quite involved, so we'll not do the full proof. We'll not do the proof of the Rogers-Ramanujan identities, but we'll show Euler's theorem using the involution principle. And if there is time, then we'll see a different proof of the Rogers-Ramanujan identity using Gaussian binomial coefficients, as well as a finite version of the Rogers-Ramanujan identity. Okay. So recall that Euler's theorem is the following. So the number of partitions into odd parts is equal to the number of partitions into even parts. The number of partitions of n into odd parts is equal to the number of partitions of n into distinct parts. Okay, and the proof is quite easy actually. So I mean, both. So as I mentioned last time, there is a bijective proof by Glacier, which is quite easy, and then the proof using generating functions is also very easy, right? So recall, I mean, how the proof went. So let's start with the generating function for partitions into distinct parts, which is this 1 plus qi product. And what we do is we multiply and divide by 1 minus q to the I in the numerator and denominator. This would give us, in the numerator we'd get 1 minus q to the 2i, then in the denominator we'll get 1 minus qi. And notice that 1 minus q to the 2i gets cancelled out with things in the new denominator, and only terms of the form 1 minus q to the 2i plus 1 or minus 1 remains in the denominator, right? And what we got in the end was the generating function for partitions into odd parts. Now, the involution principle, which was given by Garcia and Milne, looks at this middle product. Okay, so they look at this middle inequality, which is basically product of two different generating functions, right? So what we do is we consider tuples of this type. So let's say psi and pi, where psi is an ordinary partition, and pi is a partition into distinct even parts. Okay? And we consider that if you add up all the parts of psi and pi, then the sum of all the parts would be n. Okay, so what we design are two involutions. So involution is any map. If you square that map, you get the identity back. So that's an involution. Okay. So we want to design two involutions on this pair of partitions. And then we state what is the general involution principle. And from there, we recover a bijective proof of Euler's result. Okay. So that's the goal. And the involutions are very easy actually. Okay. So let's start with the first involution, which we call alpha. So let's say alpha takes some psi and pi, and if alpha acts on that, it takes it to some psi prime, pi prime. Okay. So what is this psi prime and pi prime? So what we do is we consider the smallest even part. Consider the smallest even part. Let's say 2 nu in this tuple that we started out with. Okay, so there will be some smallest even part because pi is a partition into distinct even parts. Okay, so it can be empty, but yeah. So we consider that smallest even part, and then what we do is say if the smallest even part is in pi, then we delete it from pi. Then we delete it from pi to form a new partition, which is pi prime, okay, which is just pi, where we have deleted this part to pi. Okay, and on the other hand, if 2 pi is not in pi, then So, well, okay, so we need to, so this now changes because once we delete, where does the part go? So then we delete it and we add the part to psi to form psi prime. Okay. So this is just, I mean, if the smallest part is in pi, the smallest even part is in pi, we just pick that even part and we put it in psi, which becomes the new psi prime. And then pi prime is just pi without the even part, 2 pi. Okay. And the next case is if 2 pi is not in pi, sorry, 2 nu is not in pi, then we delete 1 2 nu from psi to form psi prime, and like before we add it to pi to form pi prime. Okay, so I mean, example, I think it's probably not even necessary, but let's see an example. Okay, so suppose our psi is something like 3 plus 3 plus 3. Okay, so this is clearly a partition into it's an ordinary partition. So if you recall, psi is an ordinary partition and pi is a partition into distinct even parts. Say, let's say pi is 2. Okay, this is clearly a partition into distinct even parts. Now if you apply alpha, this map that we just designed on psi pi, what we'll get is, since the smallest even part, which is 2, belongs to pi, we are just going to remove that part from pi and put it in psi. So that means we'll have 3 plus 3 plus 3 plus 2, and this will just be the empty set. Okay, so this is how it works, right? And now if you think about this, so if you apply, so let's call it psi prime and pi prime. Now if we apply alpha to psi prime and pi prime, then we see that the smallest even part is in psi prime, so we are going to remove that part and put it in pi prime. Okay, so we'll get 3 plus 3 plus 3 comma 2. So you see that applying the map twice gives us back what we started out with, right? So this means that clearly alpha square is equal to the identity map, and hence alpha is an involution. Okay. And this is the first involution. Okay, so it's pretty easy. I mean, you just pick the smallest even part and then you move it to the other partition. Okay, that's it. The second involution is similar. Okay, but instead of considering our smallest even part as 2 pi, we are going to consider the smallest even part as 2 nu. We are going to consider the smallest even part as nu plus nu. Okay, the second involution, then let's call it beta. So we are going to define some beta again on pair of partitions psi pi, and we'll get psi prime pi prime. Okay, so you are going to again consider the smallest even part, but as I mentioned, this time the smallest even part 2 nu, we are going to consider it as a doublet, so like nu plus nu. Okay. So consider the smallest even part, so nu plus nu. Okay, and again similar, so if nu plus nu is in pi, then delete it from pi to get pi prime, and add nu plus nu to psi to get psi prime. Okay, and on the other hand, if nu plus nu is not in pi, then we delete it from psi to form psi prime and add it to pi to form pi prime. Okay, it's very easy. So suppose we start out with, say, my psi is say 3 plus 3 plus 3 plus 1 plus 1, and say my pi is empty. Okay, so what would be now beta applied to this psi pi? We'll see that clearly. I mean, the smallest doublet nu plus nu is 1 plus 1 here, right? And this is in psi. So what we're going to do is we're going to pick this 1 plus 1 doublet from psi and put it into pi. In that case, what we'll get here is we'll have 3 plus 3 plus 3, and then this 1 plus 1 will become 2. Okay. And again, I mean, if you apply this once more, then you should get the identity back, okay? Because the smallest even part, which is 2, you write it as 1 plus 1, and then you move it from pi into psi. So again, beta is an involution. Okay. Now the question that we are interested in are, what are the fixed points of this involution, okay? That means if you apply that involution to that particular point, it does not change. These are called fixed points. Okay. So the question is, what are the fixed points? Of this involution, of these involutions, okay? Both the involutions, right? So if you think about this, the answer is not very difficult, okay? So the answer for alpha, these are, I mean, so for alpha, these are all those psi and pi where pi is equal to the empty partition and psi is just a partition into odd parts, okay? Because if you apply alpha to these kind of partitions, then there is no even part, so you are basically not changing anything, so you just get back the same thing, right? And for beta, this will be exactly those partitions where these are all those psi and pi, where pi is again the empty partition and psi is a partition into distinct parts. So if you think about this, in this case, if the parts in psi were not distinct, that means some part repeated, then that would be this doublet, nu plus nu. Okay. In that case, you would have clubbed this nu plus nu together and put it into the nu pi. Okay. So the only fixed point for beta would be these type of partitions where pi is empty, but psi is a partition into distinct parts. Now you can see that the fixed points of these involutions alpha and beta actually give us the two sides of Euler's identity, right? Partition into odd parts and partition into distinct parts. So this brings us to the involution principle. Okay? I'm going to state the involution principle, and it might look very artificial and complicated, but in some sense it's quite natural if you work out the proof. The proof I'm not going to do. I mean, it's not difficult, but we are not going to do the proof. I'll give you a reference for the proof. So what is the Garsia-Milne involution principle? And as I mentioned, this is of wide applicability. It's not only applied in partitions, but it has applications outside partitions as well. Okay. So let me state the involution principle. So we start with some C set, which is say C plus union C minus, with intersection being empty. Okay, so intersection of C plus with C minus is empty. So that means C is a disjoint union of the components C plus and C minus. All right, and B2 involutions on C such that each of the fixed points lie in C plus. Okay, and let F alpha and F beta be the fixed point set. That means it contains all of the fixed points of the involution alpha and the involution beta. So be the fixed point set of alpha and beta, and we have the following. So we have two conditions. So what this says is that outside these sets, so that means if you take C plus and then take away everything that is in F alpha. So remember F alpha, so if you take C plus and you take out F alpha, then everything on that, if you apply alpha, it should be in C minus. Okay, so it says alpha applied to C plus minus F alpha is lying between C minus, and if you apply alpha to C minus, it lies in C plus. Okay, and similarly beta, C minus minus F beta lies in C plus, and if you apply beta to C minus, it should lie in C plus. Okay, so if this happens, then either a cycle of the permutation alpha beta contains no fixed points, of either alpha and beta, or it contains exactly one element of F alpha and one of F beta. So it either contains no fixed points of either alpha and beta, or it contains exactly one from each. Contains exactly one element of F alpha and one of F beta. Now the goal for us is to show that the involutions that we created, these are actually what we have here, okay, in this involution principle. So we want to apply this to Euler's theorem. Okay, so here in our case, C is just, you know, the set of all pairs of psi pi, like we had before. Okay, where pi has only distinct even parts and psi is an ordinary partition, and if you sum up all the parts of psi and pi, you get n. Okay, then what is C plus? So we want to partition the set C into C plus and C minus. So this will be now in terms of the number of parts. Okay, so C plus is the set of all pairs psi pi where pi has an even number of parts. And as you can guess, C minus is the set of all pairs psi pi where pi has an odd number of parts. Okay, now this is a proper partition of C. So any partition pi into distinct even parts can have either odd number of parts or even number of parts. And this is going to be disjoint as well, because no partition can have even number of parts as well as odd number of parts, right? So this condition, the first condition in our in our involution principle, which was that C plus intersection C minus should be empty, is satisfied. Okay, so also, I mean, you need some C such that C plus union C is C plus union C minus, and it should be disjoint. So this is fine. Then what is F alpha? Okay, so we have already seen, right? This is equivalent to partitions of n into odd parts. And F beta we have seen, so F alpha is the set of fixed points, and we saw that the fixed point of alpha are exactly those where psi is a partition into odd parts and pi is empty. Okay, and F beta is equivalent to the partitions of n into distinct parts. Again, similarly, F beta is the set of fixed points of beta, the involution beta, right? Now think for a, so we want to verify these inequalities now. Okay, sorry, not inequalities, these properties. We want to verify if these properties are satisfied or not. Okay, so let's see the first one. Okay, and then I'll leave the rest for you. So we want to see what is alpha applied to C plus minus F alpha. Okay, so if you think about this, we really change the number of parts. Okay, so yeah, so you see, if you apply alpha to whatever is in C plus minus F alpha, it should lie in C minus. And now the way that we have constructed C plus and C minus is that the number of parts are different, right? C plus is the set of all pairs where pi has an even number of parts, and C minus is the set of all parts where pi has an odd number of parts. And now f alpha, where those partitions where pi is empty, so you take out all those, and then in C plus, now you have partitions where, sorry, you have these pairs where psi can be an ordinary partition, but it is not a partition into odd parts. So that means there exists some even part. Okay, so what we are basically doing is, wherever that even part is, there exists some even part. We are just taking that even part and putting it either into pi, which increases the number of parts by 1 for pi, or we are removing it from pi and putting it into psi, which decreases the number of parts in pi. So in either case, the number of parts in pi is either decreased or increased by 1. And if you start with a partition of pi into even parts, so where the number of parts is even, then if you increase it, it becomes a partition where the number of parts is odd. And if you decrease it, then it becomes a partition where the number of parts is odd again. And similarly for the other case, right? Just a second, let me share the screen. So I'll tell this once again, but I think it is probably clear. So you see what is in, so in this case, these are all, I mean, you forget about what is in psi for the moment. This is everything with pi equal to empty set. And this psi is now only odd parts. Okay. So if you take C plus minus F alpha, then it is guaranteed that there is an even part. Okay. So either in psi it is guaranteed or it is in pi. Now if you apply alpha, then you are changing the number of parts in pi by 1 or minus 1. So what we have here is that it should be in C minus. Okay, because C plus contains all partitions where pi has an even number of parts. And if you're changing the number of parts, either plus 1 or minus 1, then it should be an even odd number of parts. So this is clearly going to lie in C minus. And the other case is pretty easy. So alpha applied to, so we need to check this part, right? So alpha applied to C minus should be in C plus, and this is clear, right? So you are anyway changing the number of parts in pi. So if you're changing it, it's either increasing or decreasing by 1. And in any case, if you start with an odd number of parts, you're going to end up with an even number of parts. So this is easy to verify. So I leave the part of verification for beta to you, but it's pretty simple and it's exactly the same. Okay. So what we have is that the conditions of the involution principle are satisfied. The conditions of the involution principle are satisfied. That means we can apply now the involution, whatever the involution principle says. And the involution principle says is that, so what is the bijection? So let me mention explicitly the bijection that the involution principle gives. Okay. So we choose some psi pi, this tuple, which is in F alpha. That means we start out with a psi and pi where pi is empty and psi is a partition into odd parts. Okay. And then we apply successively this. So, and apply successively the permutation alpha beta. Okay, so you apply alpha, then beta, alpha, then beta, alpha, then beta, and so on. Okay, then by the involution principle, there is some principle, there is some unique psi prime and pi prime, which is in F beta, that must lie in this cycle. Okay? And what are the elements of F beta? These are exactly the elements where the first partition in the tuple is a partition into distinct parts and pi is empty. So that means we have converted a partition into odd parts to a partition into distinct parts. And we can see an example. So this is the bijection, and this is actually equivalent to Glaisier's bijection, which I did not mention properly. But if someone knows, this is equivalent to Glaisier's bijection. Okay. So let's look at an example that we started off with. All right. So I have an example here, which is this. So you start with 3 plus 3 plus 3 plus 1 plus 1 and the empty. So this is some partition, okay? And this is a partition in F alpha, clearly, because the first tuple, the first component is a partition into odd parts, okay? So we are going to apply the map beta now. And if we apply the map beta, you know what happens. So this 1 plus 1 gets clubbed together into a 2, and then it moves to the other side. So we'll have 3 plus 3 plus 3, comma 2. Okay. Then we apply the map alpha, and we see that the smallest even part is 2, which is in pi. So we move it to side. So this is 3 plus 3 plus 3 plus 2, comma, the empty partition, yeah. Next, we apply again beta, and we see that the smallest even part, in this case, the doublet is 3 plus 3, okay? So we pick this 3 plus 3 and we move it to the other side. So we get 3 plus 2, and 3 plus 3 becomes 6. Then again we apply alpha, and this time the 2 shifts to the other side. So we get 3 comma 6 plus 2. We apply beta again, and if we apply beta, we shift the 2. So which is now the smallest even part is in pi, which is 1 plus 1. So we shift it and we get 3 plus 1 plus 1 comma 6. And finally, if we apply alpha here, I think you need 2 more steps. So if we apply alpha here, then the 6 shifts to the other side. So you have 6 plus 3 plus 1 comma the empty partition. Apply beta once again, and this 1 plus 1 shifts to the other side. So you get 6 plus 3 comma 2. And finally you apply alpha, then the 2 shifts to the other side. 6 plus 3 plus 2 comma 5. And we stop. So we have reached a partition where the first component is a partition into distinct parts. So we see clearly, right? So we started out with a partition into odd parts, and we reached a partition into distinct parts. And if you know how Glacier's bijection work, this is exactly what you would have got using Glacier's bijection. Okay. So as I mentioned, the proof is not difficult, but we are not going to do the proof. So I just wanted to give you an idea of what the involution principle does. Okay. So it's sort of a zigzag motion. So what you did here was basically you started out. So these are some 2 sets, let's say, okay, and you applied alpha, then beta, then alpha, and so on, okay, and this is how you did, and eventually you are guaranteed to end up with something which you want. Basically, in this case, we wanted a partition into distinct parts. So the involution principle guarantees that we'll reach somewhere there. Okay. All right. So I hope this technique is clear. So if you want to see a proof, an easy proof, this is in Andrew's monograph on Q series. I think it's in the development of Q series or applications of Q series in number theory, partitions, and so on. And it should be in the chapter related to the Rogers-Ramanujan identities. Okay. All right. So any questions about this? Okay. So we want to start a new topic now. So now we are going to stop with the combinatorial aspects of the Rogers-Ramanujan identity, and we'll go back to now the analytic aspects once again. In particular, we want to see 2 different proofs of the Rogers-Ramanujan identity. The first proof that I want to show you involves the Q binomial coefficients that we defined long back, if you remember. So let's recall those Q binomial coefficients. So you had this binomial coefficient, and the Q version was just QQN divided by QQM times QQN minus M. Okay. So this was called the Q binomial coefficient. And the thing is that if you take, so we need to exploit 2 different properties of this. Okay. So first thing is that if you take Q goes to 1, then this becomes the normal binomial coefficient. But now I want to take the limit as n goes to infinity of this. What happens then? So if n goes to infinity, then this QQN in the top and QQN minus M in the bottom cancels out. Okay, this becomes QQ infinity. So what I have remaining is just 1 over QQM. Now the second thing that I want to notice is that suppose I have something like R times N plus M1 and S times M plus M2. Sorry, S times N plus M2. Okay. Then I want to take the limit as n goes to infinity. Now, this is the same thing as taking limit as n goes to infinity. By the definition, this is just q rn plus m1 divided by q sn plus m2 times q n times r minus s plus m1 minus m2. Okay, so this is just the definition. And this time, if you notice, then two terms will get cancelled out, but one term will remain, and that term, since n is going to infinity, and in each of this term there is this n, so the base is always going to infinity in each of these. So that means the two q infinities get cancelled out, and you will be left with 1 over q infinity in this case. Okay. So we need these two. So we need to keep in mind these two. So let's call it equation 1 and equation 2. Now, I want to state a finite version of the Rogers-Ramanujan identity. Finite in the sense that if you take limit as n goes to infinity for the identity that I'm going to state, you recover back the two Rogers-Ramanujan. Let's see what those two finite identities are. Okay. So this is a theorem. This is due to Andrews and Schur. Okay. So two parts, because you have two Rogers-Ramanujan identities. Q j square n minus j, choose j sub q, and this is equal to j goes from minus infinity to infinity, minus 1 raised to the j, q raised to the j, 5j plus 1 over 2, 10 minus 5j. So it looks complicated. First, we'll see how these two identities actually give the two Rogers-Ramanujan identities. Okay, and it's quite easy so to notice this. Okay, so these are finite versions of the Rogers-Ramanujan identity. You can see already some of these coefficients which are here. So this q power appears in the first Rogers-Ramanujan identity, and this q power appears in the second Rogers-Ramanujan identity, right? And this looks very similar to how the Jacobi's triple product identity is. Okay? Appropriate substitution of the Jacobi's triple product identity should give something here. So, and that turns out to be true. So we take limit as n goes to infinity. Okay, and we'll use these two identities that we have. Okay, so number 1 and 2. So what happens in the first case? Okay, so we can write both of these together. Okay, so let me write down the left hand side, right? So left hand side is just summation q raised to the power j square plus, let's say, aj n minus j q, where a is equal to 0 and 1. So if it is 0, then we get the left hand side of the first identity, and if it is 1, we get the left hand side of the second identity. Okay, and we want to take, so actually we want to take the limit. So I should have written limit of left hand side. So I want to take the limit as n goes to infinity of this. Okay, and if I do that, so the limit goes inside. So I have qj square plus aj, and this is limit n goes to infinity of n minus j q. And now we see that this is exactly what we had in the first equation, right? So this was, we are in this case, okay? And the limit in this case was 1 over q m. So we'll have the limit 1 over q j. So this is nothing but qj square plus aj divided by q j. And clearly, this is the left-hand side of the Rogers-Ramanujan identity. For a equal to 0, this is the left-hand side of the first Rogers-Ramanujan identity. Or for a equal to 1, this is the left-hand side of the second Rogers-Ramanujan identity. So we hope that if you take limit n goes to infinity for the right-hand side, it should give us the product side of the Rogers-Ramanujan identity. And that is true. So let me take the limit. Okay. So again, we can write this together. So if you notice inside, if you take limit as n goes to infinity, the only things for which we need to care are these, right? So these things we need to care only about these two q binomial coefficient, because there is no n otherwise. And for that, we'll use now the second identity here. Okay. And we will get a 1 over q infinity. So I'm not going to do it, but I'm just going to write what you get. So again, taking limit n goes to infinity on the right hand side and using 2, we get, so again I'm going to write it together, okay, both the things. So we get this 1 over q infinity comes out, and then you have j from minus infinity to infinity, minus 1 raised to the power j, q raised to the power j times 5j plus 1 over 2 minus 2aj. Okay. And now we will use Jacobi's triple product identity. So recall, I mean, you have used this several times, but let me just write it. Recall what is Jacobi's triple product identity. So the form that I want to use is the following. So let's say I going from 1 to infinity, 1 minus q to the 2i, 1 plus z times q to the 2i minus 1 times 1 plus q to the 2i minus 1 over z. And this would give us this sum. So say I going from minus infinity to infinity, z to the I, q to the I squared. Okay, so this is the form of the Jacobi's triple product identity that I want to use. Now, what should be my choice of, so I want this thing, the sum thing. So I want this thing to be equivalent to this sum here. Okay, so clearly I need 1 minus. So what I do is set z equal to minus q raised to the power 1 minus 4a by 2, and q is now set to q raised to the power 5 by 2. So if I do that, let me show you the calculation quickly. So z to the I just becomes minus 1 raised to the I, q raised to the I times 1 minus 4a by 2, and q to the I square just becomes plus 5 by 2 I square. Okay, here. And if you do the calculation, so you can easily see. So this 5 by 2 I square just appears here. Okay. And then this 1 by 2 I is this term 1 by 2 I. And then this 2a gets cancelled out. So sorry, 4a gets cancelled with the 2. So this quantity along with this becomes 2ai, which is this. Okay. So the index is just I is now changed to j. So that means this side is equal to this side with these special values. Okay. So we want to figure out what is this now. So if you think about it, this is nothing but q. So I mean, it became a bit messy, but I hope you will understand. So using Jacobi's triple product identity, then the right hand side now becomes 1 over q infinity times q5 infinity, and then for a equal to 0, this will be q3 q5 infinity, and for a equal to 1, it will be q1 q5 infinity. So together we can write it as something like this, and this will be q2 plus 2a comma q5 infinity. Okay, and that's it. These are the Rogers-Ramanujan identity. Because this q infinity, you can write it as q5 infinity, q square q5 infinity, and so on. Then many things will cancel out. So you will just have two factors in two products, q products in the bottom. For a equal to 1, you will get the first Rogers-Ramanujan, right hand side of the first Rogers-Ramanujan identity, and for a equal to 1, you will get the right hand side of the second Rogers-Ramanujan identity. So, so far, I think it should be clear that this finite form of the Rogers-Ramanujan identity, if you take limit as n goes to infinity, it actually gives us the two Rogers-Ramanujan identities. Now, all we need to do is prove this finite form, and then we'll be done, right? So the proof, so it involves, showing that both the right-hand side and the left-hand side satisfies the same recurrence. And we are going to show that one side satisfies this recurrence, the other side, I'm going to leave it for you. But why don't I do it? So why don't I do it next time? Okay, so this time we'll just stop here. And in the next time, we'll see how to give a proof of this finite form of the Rogers-Ramanujan identity. So if you have any questions, then I am happy to answer.